Fact number 1. While it is true that if a circuit is not needed for an item, it is not likely to become energized, there are exceptions. For example, a non-electrical metal piping system connected to a grounded electrical system could become energized through fault currents. A metal structure located near power lines or other energized equipment could become energized through electrostatic induction. Fact number 2. While the equipment grounding conductor may serve as the bond for items mentioned, it is not always the case. For example, gas piping systems may require a separate grounding electrode system, especially in areas with lightning activity. Metal structures that are not connected to the electrical system may still require bonding to prevent static charges from accumulating. Regarding circumstances where facts 1 and 2 will not rule. Firstly, non-electrical metal items connected to grounded electrical systems. As mentioned in fact number 1, fault currents can cause non-electrical metal items to become energized. Secondly, metal structures in proximity to energized equipment, even if these structures do not have an electrical connection, electrostatic induction can still cause them to become energized. Thirdly, electrical circuits installed in non-metallic buildings. In these cases, the equipment grounding conductor may not provide sufficient grounding protection. The rules pertaining to items likely to become energized are necessary to ensure the safety of personnel and property. They require bonding and grounding of all metal items that could potentially become energized, even if they are not directly connected to an electrical system. In conclusion, the rules for items that are likely to become energized are not a non-issue. They are essential for ensuring the electrical safety of buildings and structures. By following these rules, electricians can prevent electrical hazards and protect life and property. Now let's delve deeper into the technical aspects of these concepts. Grounding and bonding are fundamental principles in electrical safety, designed to minimize the risk of electric shock and fire. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to operate and clear the fault. Bonding ensures that all metal parts within an electrical system are at the same electrical potential, reducing the potential for shock hazards if someone comes into contact with two different metal surfaces. When we talk about metal objects that may become energized, we're addressing situations where a conductive object, not normally carrying current, could inadvertently become energized due to a fault condition or other external influence. This is where the rules regarding likely to become energized come into play. Let's consider the case of a non-electrical metal piping system connected to a grounded electrical system. If a fault occurs within the electrical system, such as a wire coming into contact with a metal enclosure, the fault current will seek the path of least resistance back to the source. If the metal piping system is connected to the grounded electrical system, it can become part of that fault current path. This can cause the piping system to become energized, creating a shock hazard if someone touches it. Similarly, metal structures located near power lines or other energized equipment can become energized through electrostatic induction. Electrostatic induction occurs when a charged object, such as a power line, creates an electric field that induces a charge on a nearby conductive object, such as a metal structure. This induced charge can cause the metal structure to become energized, even if it is not directly connected to the electrical system. To mitigate these risks, the National Electrical Code, which is referred to as the NEC, requires bonding and grounding of all metal items that could potentially become energized. Bonding involves connecting all metal parts together to create a common ground potential. This ensures that if one metal part becomes energized, all other connected metal parts will also be at the same potential, reducing the risk of shock. Grounding involves connecting the bonded metal parts to the earth through a grounding electrode system. This provides a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. The equipment grounding conductor, or EGC, plays a crucial role in this process. The EGC is a conductor that connects the metal enclosures of electrical equipment back to the grounding bus at the service entrance. It provides a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. In some cases, the equipment grounding conductor may serve as the bond for metal items that could potentially become energized. However, this is not always the case. For example, gas piping systems may require a separate grounding electrode system, especially in areas with lightning activity. Lightning strikes can induce high voltages in metal piping systems, creating a shock hazard. A separate grounding electrode system can provide a low impedance path for lightning current to flow to ground, protecting the piping system and nearby personnel. Metal structures that are not connected to the electrical system may also require bonding to prevent static charges from accumulating. Static charges can build up on metal structures due to friction or other factors. If these static charges are not dissipated, they can create a spark hazard, potentially igniting flammable materials. Bonding the metal structure to ground can help to dissipate these static charges, reducing the risk of fire. In non-metallic buildings, the equipment grounding conductor may not provide sufficient grounding protection. Non-metallic buildings do not have a conductive metal frame that can serve as a grounding path. In these cases, additional grounding electrodes may be required to provide adequate grounding protection. The size and type of grounding electrode required will depend on the size and type of electrical system, as well as the soil conditions at the site. It's important to consult the National Electrical Code, NEC, and local electrical codes for specific requirements. The National Electrical Code, NEC, provides detailed requirements for grounding and bonding electrical systems. These requirements are based on years of experience and research, and are designed to ensure the safety of personnel and property. Some key sections of the NEC related to grounding and bonding include Article 250, which covers grounding and bonding in general, Article 300.3b, which requires all circuit conductors, including the equipment grounding conductor, to be installed together in the same raceway or cable, Article 408.41, which requires all metal parts of switchboards and panel boards to be bonded together and connected to a grounding electrode conductor, and Article 547.9, which provides specific requirements for grounding and bonding in agricultural buildings. When installing grounding and bonding systems, it's important to use appropriate materials and techniques. Grounding electrodes should be made of corrosion-resistant materials, such as copper or galvanized steel. Bonding conductors should be sized according to the requirements of the National Electrical Code, NEC, and should be securely connected to the metal parts being bonded. All connections should be made using approved connectors and fittings. Regular inspection and maintenance of grounding and bonding systems is also essential. Grounding electrodes should be checked periodically to ensure that they are still in good condition and are providing a low impedance path to ground. Bonding connections should be inspected to ensure that they are tight and free of corrosion. Any damaged or corroded components should be replaced immediately. It is important to understand the role of overcurrent protection devices such as circuit breakers and fuses. These devices are designed to protect electrical circuits from overloads and short circuits. When a fault occurs, the overcurrent protection device will trip, interrupting the flow of current and preventing damage to the electrical system and connected equipment. Proper grounding and bonding are essential for overcurrent protection devices to function correctly. If the grounding and bonding system is not properly installed, the fault current may not be high enough to trip the overcurrent protection device, creating a fire hazard. Here are some examples of situations where proper grounding and bonding are critical. Firstly, in a residential setting, the metal enclosures of appliances such as refrigerators, washing machines, and dryers must be properly grounded to protect against electric shock. Secondly, in a commercial building, the metal conduit and junction boxes that contain electrical wiring must be properly bonded to prevent voltage differences and reduce the risk of fire. Thirdly, in an industrial facility, the metal frames of machinery and equipment must be properly grounded to protect against electric shock and prevent damage to sensitive electronic components. The concept of impedance is also very important in grounding and bonding. Impedance is the opposition to the flow of alternating current. A low impedance grounding path is essential for ensuring that fault current can quickly and easily return to the source, allowing overcurrent protection devices to operate and clear the fault. Factors that can affect the impedance of a grounding system include the size and type of grounding conductors, the length of the grounding conductors, the quality of the connections, and the soil conditions at the site. To minimize impedance, it's important to use appropriately sized grounding conductors. Keep the grounding conductors as short as possible, make sure all connections are clean and tight, and ensure that the soil has a low resistivity. Soil resistivity is a measure of how well the soil conducts electricity. Soil with high resistivity will impede the flow of current, making it more difficult to achieve a low impedance grounding path. Factors that can affect soil resistivity include the moisture content of the soil, the type of soil, and the presence of salts or other minerals in the soil. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to treat the soil with chemicals to reduce its resistivity. In addition to grounding and bonding, surge protection is also an important aspect of electrical safety. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power line switching. Voltage surges can damage or destroy sensitive electronic equipment such as computers, televisions, and appliances. SPD work by diverting the surge current to ground, preventing it from reaching the protected equipment. SPD should be installed at the service entrance and at any branch circuits that serve sensitive electronic equipment. Proper grounding and bonding are essential for SPD to function correctly. The SPD must be properly grounded to provide a low impedance path for the surge current to flow to ground. The electrical inspector plays a vital role in ensuring that grounding and bonding systems are properly installed. The electrical inspector is responsible for reviewing electrical plans, inspecting electrical installations, and ensuring that they comply with the National Electrical Code, NEC, and local electrical codes. The electrical inspector will typically check the size and type of grounding conductors, the quality of the connections, and the location of grounding electrodes. They may also perform tests to verify the impedance of the grounding system. It's important to work closely with the electrical inspector to ensure that your grounding and bonding system is properly installed and meets all applicable requirements. Common mistakes to avoid when installing grounding and bonding systems are firstly, using undersized grounding conductors. Secondly, making loose or corroded connections. Thirdly, failing to properly bond metal parts. Fourthly, not providing adequate grounding for sensitive electronic equipment. Fifthly, neglecting to inspect and maintain grounding and bonding systems regularly. By avoiding these common mistakes, you can help to ensure the safety and reliability of your electrical system. To elaborate further, let's discuss specific scenarios and applications of grounding and bonding. In healthcare facilities, grounding and bonding are especially critical due to the presence of sensitive medical equipment and the potential for patients to be more vulnerable to electric shock. Healthcare facilities typically have stringent requirements for grounding and bonding, including isolated power systems and equipotential grounding. Isolated power systems are designed to prevent leakage current from flowing to ground, which can be particularly dangerous for patients who are connected to medical equipment. Equipotential grounding involves bonding all metal parts within a patient care area to a common ground point, minimizing voltage differences and reducing the risk of shock. In industrial environments, grounding and bonding are essential for protecting workers from electric shock and preventing damage to equipment. Industrial facilities often have large electrical systems with high voltages and currents. Proper grounding and bonding are necessary to ensure that fault currents can be quickly and safely cleared, minimizing the risk of electrical hazards. In addition to grounding and bonding, industrial facilities may also use other safety measures, such as lockout/tagout procedures and arc flash protection, to protect workers from electrical hazards. In agricultural buildings, grounding and bonding are important for protecting livestock from electric shock and preventing fires. Agricultural buildings often have harsh environments with moisture, dust, and corrosive chemicals. These conditions can accelerate the deterioration of electrical equipment and increase the risk of electrical hazards. Proper grounding and bonding are necessary to ensure that electrical equipment is properly protected and that livestock are not exposed to dangerous voltages. Specific requirements for grounding and bonding in agricultural buildings are found in Article 547 of the National Electrical Code, NEC. In telecommunications systems, grounding and bonding are essential for protecting equipment from damage due to lightning strikes and power surges. Telecommunications equipment is often very sensitive to voltage fluctuations and can be easily damaged by surges. Proper grounding and bonding are necessary to divert surge currents to ground, protecting the equipment from damage. Telecommunications systems also often use surge protection devices, or SPDs, to provide additional protection against voltage surges. Let's talk about the evolution of grounding and bonding practices. Grounding and bonding practices have evolved significantly over time, driven by advances in technology and a better understanding of electrical safety. In the early days of electricity, grounding was not always considered to be essential. However, as electrical systems became more complex and the risks of electric shock and fire became more apparent, grounding practices began to improve. The National Electrical Code, NEC, was first published in 1897 and has been updated regularly since then to reflect the latest knowledge and best practices for electrical safety. Over the years, the NEC has added more detailed requirements for grounding and bonding and has expanded the scope of these requirements to cover a wider range of electrical systems and applications. One of the key developments in grounding and bonding practices has been the introduction of the equipment grounding conductor, or EG. The equipment grounding conductor provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault. The use of equipment grounding conductors has significantly improved the safety of electrical systems. Another important development has been the recognition of the importance of bonding. Bonding ensures that all metal parts within an electrical system are at the same electrical potential, reducing the potential for shock hazards. Bonding practices have become more sophisticated over time with the development of new bonding techniques and materials. Today, grounding and bonding are considered to be essential for electrical safety and are required by the National Electrical Code, NEC, and local electrical codes in virtually all electrical installations. As technology continues to advance, it is likely that grounding and bonding practices will continue to evolve to meet the challenges of new electrical systems and applications. Now, let's address some frequently asked questions about grounding and bonding. Firstly, what is the difference between grounding and bonding? Grounding provides a low impedance path for fault current to return to the source, while bonding ensures that all metal parts are at the same electrical potential. Secondly, why is grounding important? Grounding is important because it helps to protect people from electric shock and prevents fires by allowing overcurrent protective devices to operate and clear faults. Thirdly, why is bonding important? Bonding is important because it reduces the potential for shock hazards by ensuring that all metal parts are at the same electrical potential. Fourthly, what is an equipment grounding conductor? The equipment grounding conductor, or EG, is a conductor that connects the metal enclosures of electrical equipment back to the grounding bus at the service entrance, providing a low impedance path for fault current to flow back to the source. Fifthly, what is a grounding electrode? A grounding electrode is a conductor that is buried in the earth and connected to the grounding system, providing a path for fault current to flow to ground. Sixthly, what is soil resistivity? Soil resistivity is a measure of how well the soil conducts electricity, and it affects the impedance of the grounding system. Seventhly, what is a surge protection device? A surge protection device, or SPD, is a device that protects electrical equipment from voltage surges by diverting the surge current to ground. Eighthly, who is responsible for ensuring that grounding and bonding systems are properly installed? The electrical inspector is responsible for reviewing electrical plans, inspecting electrical installations, and ensuring that they comply with the National Electrical Code, NEC, and local electrical codes. Ninthly, what are some common mistakes to avoid when installing grounding and bonding systems? Common mistakes include using undersized grounding conductors, making loose or corroded connections, failing to properly bond metal parts, and not providing adequate grounding for sensitive electronic equipment. Tenthly, where can I find more information about grounding and bonding? You can find more information about grounding and bonding in the National Electrical Code, NEC, and in various textbooks and online resources. Let's explore some advanced topics in grounding and bonding, including the use of impedance grounding systems and the challenges of grounding in data centers. Impedance grounding systems are used in some industrial applications to limit the amount of fault current that flows during a ground fault. In a solidly grounded system, the fault current can be very high, which can cause damage to equipment and create a safety hazard. In an impedance-grounded system, a resistor or reactor is inserted in the grounding path to limit the fault current. This can reduce the risk of damage to equipment and improve safety. However, impedance grounding systems also require more sophisticated monitoring and control systems to detect and clear ground faults. Grounding in data centers presents unique challenges due to the high density of electronic equipment and the sensitivity of this equipment to voltage fluctuations. Data centers typically require very low impedance grounding systems to minimize noise and ensure the reliable operation of equipment. This can be achieved by using a combination of techniques, such as installing a grid of grounding conductors under the floor, using isolated ground receptacles, and providing dedicated grounding paths for sensitive equipment. Data centers also often use surge protection devices, or SPDs, to protect equipment from voltage surges. The Telecommunications Industry Association, which is referred to as the TIA, has developed standards for grounding and bonding in data centers. These standards provide guidance on how to design and install grounding systems that meet the specific needs of data centers. The ongoing research and development in grounding and bonding, which is aimed at improving the safety and reliability of electrical systems. Researchers are constantly working to develop new grounding techniques, materials, and equipment. One area of research is focused on developing more effective grounding electrodes. Traditional grounding electrodes, such as ground rods, can be difficult to install in certain soil conditions. Researchers are exploring the use of alternative grounding electrodes such as chemical electrodes and concrete-encased electrodes, which may be more effective in these situations. Another area of research is focused on developing better methods for detecting and clearing ground faults. Traditional ground fault protection systems can be slow to respond, which can increase the risk of damage to equipment and safety hazards. Researchers are exploring the use of advanced ground fault protection systems that can detect and clear ground faults more quickly and reliably. In addition to research and development, there is also ongoing work to improve the National Electrical Code (NEC) and other electrical codes and standards. The NEC is updated every 3 years to reflect the latest knowledge and best practices for electrical safety. The code-making process involves input from a wide range of stakeholders, including electrical engineers, contractors, inspectors, and manufacturers. The goal of the code-making process is to develop codes and standards that are both safe and practical to implement. It's crucial to stay updated with the latest codes and standards, which is important for all electrical professionals to stay up to date with the latest codes and standards. This can be achieved by attending training courses, reading industry publications, and participating in professional organizations. By staying informed, electrical professionals can ensure that they are using the best practices for grounding and bonding and that they are providing safe and reliable electrical systems. Proper grounding and bonding are not just about complying with codes and standards, they are about protecting people and property from electrical hazards. By understanding the principles of grounding and bonding and following the best practices, you can help to create a safer electrical environment for everyone. It's also important to remember that grounding and bonding are not a one-time task. Grounding and bonding systems should be inspected and maintained regularly to ensure that they are functioning properly. Grounding electrodes should be checked periodically to ensure that they are still in good condition and are providing a low impedance path to ground. Bonding connections should be inspected to ensure that they are tight and free of corrosion. Any damaged or corroded components should be replaced immediately. By taking these steps, you can help to ensure that your grounding and bonding system will continue to provide reliable protection for years to come. Remember to always consult with a qualified electrical professional for any questions or concerns about grounding and bonding. Electrical work can be dangerous, and it is important to have the expertise of a qualified professional to ensure that the work is done safely and correctly. Do not attempt to perform electrical work unless you are properly trained and qualified.